So this may be the hardest thing you've done. It depends on how well your brain does this kind of thing. So if you'll notice, here we have homework 35. Page 770, numbers 1 through 17 odd must be done in the format from class. That is, I'm going to be very explicit about a format that I want for this. And there is rhyme to my reason to my rhyme. I always say rhyme to my reason. There is a reason behind it because this is the way I was taught how to do it. And when you're first learning how to do it, it makes sure that you're checking all the boxes. And so it's once you get really good and move on into the future of your mathematical career, then you can start cutting some corners. But this way that I'm going to tell you to do it will help you to make sure that you're not cutting any corners. So, without further ado, this is what we're talking about today. Mathematical induction. You've heard of deductive reasoning, like Sherlock Holmes. Induction.
It's like the other way around.
Kind of the other way around, and you'll see what's going on. But first, so for the conversation today, okay, we're going to, this is just going to be constant throughout everything we talk about. We're going to suppose that n is a positive integer. That is, and what I'm going to write a bunch of times is just n is bigger than 0. And so we're going to understand that this means n is an integer and it's bigger than 0. So that is n is equal to 1, 2, 3, and so on, right?
So the
natural numbers. I could have also said n is a natural number. But sometimes natural numbers include 0, whatever, right? So positive meaning strictly positive. Although, like in practice, now that's not always going to be the case. N can be 0 sometimes. It's fine. It's just for what we're doing today. This is what we're going to do, okay? So suppose that n is a positive integer and that p sub n is a mathematical statement. Involving n. Okay. For instance, Pn could be the statement that, say, 1 plus 2 plus all the way up to n is equal to n plus 1 all over 2. You guys remember that? How we proved that before? Now, this is proved. We have proved this in class. I showed you how to, and there's this nifty little trick, right? We said, let y or whatever it is equal 1 plus 2 all the way up to n. And then we did the same thing, but we did it backwards, right? And then added them together. And it's cool that there was this nifty little trick that you could pull to actually derive this yourself. But what if you didn't know that trick, and I told you, prove this? Good luck, right? Well, with mathematical induction, that's how you, and we will prove this one using mathematical induction. To be clear, we've already proved this. This is already true, but just for instructional purposes, we're going to go do it again with mathematical induction. Now, to be clear, what I mean by this, all of this symbolism and everything like that, P1 would be the statement 1, I guess that's it, equals 1 times 1 plus 1 over 2. Is that true?
Yeah.
Yeah, that's true. P2 would be what?
2 times 2 plus
Whoa,
1.
whoa, 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 whoa.
Oh, 1.
Yeah, it's the whole statement. The whole statement is this thing.
So 1 plus 2 equals
1 plus 2 equals
2 times 2 plus 1 over
2 plus 1 over 2, right? That would be that statement. Is that true?
Yes.
All right, because that's 3. That's 2 divided by 2 is that. 2 plus 1 is 3. Okay, yeah, it's true. Now, P3, I just want to do this here. P3 would be what?
1 plus 2 plus 3.
There you go. 1 plus 2 plus 3 equals
3 times 3 plus 1 over 2.
And is that true?
Yeah.
Okay, so here's the thing. No, I don't want to do it that way. We'll do it this way. I'm going to tell you what the principle of mathematical induction is. Okay? Here we go. Principle. Principle. Yeah. I always want to spell it principal, you know. Principle of mathematical induction. Okay, so this is kind of like your definition for this. Given statements, Pn. Okay. Given statements Pn. Here we go. If, and two things have to be true. If, in the first place, if P1 is true, and here's the second part, if for all k, okay, for all integers k. So when I do this in this lecture here, we're talking about if I'm using n or k, I'm talking about an integer, and here we're talking about positive k's. So if it's true that for all k is bigger than 0, here's the statement. Here's the statement. If pk is true, then pk plus 1 is true. So this is weird because we have a bunch of ifs in here. Let's make sure we have this out. So if, and then I have this big old statement, and I'm going to have a big then after all of that. But here, these two things have to be true. What has to be true? P1 has to be true. And it has to be the case that for all of these guys, you'll notice kind of like this. For all k bigger than 0, this is true, but it's not just that. It's that we have to show that if one of them is true, then the next one is true. And if you could get both of these guys, then every Pn is true for all n bigger than 0. Does this make sense? Yeah. Right, so basically what we're doing is if we could show that some general one, and notice I didn't say that P2 is true, then P3 is true. Because that's not what we want. It might be the case that P2 is true and P3 is true, but we have to show that this one implies this one. Like what we're doing here, you'll notice, you say P1 is true, yep, and P2 is true. Okay, P3 is true. Cool. So can we conclude that all of the rest are true? No, because, and I want to be very explicit about this. So here's this. This is what we're working with, and I do want to get. Let's do it this way. Here's another statement. Pn. Here's the mathematical statement that sine n is bigger than 0. Now you might say, well, okay, let's check it out. Is P1 true? When I plug in a 1, is it true that sine 1 is bigger than 0? Yeah. Yep, it sure is, because let's think about what sine looks like, right? Sine, right? There's pi. And so when you plug in a 1, it's positive. Yep, it's true. So you might say, okay, is P2 true? Is sine 2 positive? Yeah, because 2 is somewhere right around here. And so you say, yep, okay, it's true. Let's do one better. P3. Is sine 3 positive?
Yes.
It is true. So can we conclude then all of them are true forever and ever? No, because if you try P4, is sine 4 positive? No, it's not. Sine 4 is actually somewhere right around here, right? Because if that's 3.14, this would be actually 4. And it would be a negative number. So it's not enough to just say, well, I got this one's true and this one's true. Okay, so it's going to just stay true forever. No, it might not. But if we could show, and this is the idea behind mathematical induction. So since obviously this is not a true statement, so we can't prove it. But with a statement like this, you could say, well, you know what? If I can show that for some general one of them, right? So if I just show pk in general, and today, in the way you're going to do this for homework, is that you're going to use the letter K to denote, let's just take any one of them. And if you could show that for any K, PK true implies that PK plus 1 is true, then all you need to say is, well, we know that P1 is true, and so P1 true implies that P2 is true. But then you use this again and say, well, we know that for any K, that implies that the next one is true. Since P2 is true, then that means that P3 is true. But since P3 is true, right, that implies that P4 is true, and on and on and on and on forever. Okay? So that's the key here. And really, you have to show that this one implies that this one is true. Otherwise, you can't just show that a couple of them are true, because obviously, as we just saw, that's not going to work for everything. But if you could show that a general one implies that the next one is true, then you could use this nifty chain effect here. Now, also, what if you show that this is true, but you can't establish that the first one's true? Well, maybe if you establish that the second one's true, then you go on and you could say 2 and so on and so forth. Or maybe if you show, well, it's true once it's 5, okay, then that's still the same principle. Technically, P1 is what we're talking about, but the idea is you have to have a base somewhere. You have to have some base truth from which all of this follows, right? Now, any questions about this? It seems pretty intuitive. Now, we cannot prove this. It requires some really, really, really heavy guns, and actually, I've taken really advanced stuff, and I've still never seen a proof of this. But do you believe it?
How would it not?
How could it not be, right? It's one of those things that it's like, well, how could it not be? Like, if you show that one of them is true, and then you've shown that this one implies that this one's true, well, then that one implies that 2 is true, and 2 implies 3, and 3 implies 4, and so on forever. So we're just going to take this as good enough, right? Are we all in agreement that this is on sound ground? Nobody doubts this? Okay. Okay, so here we go. This is where you're going to really hate me, because I'm going to demand that you do it in this format here. Now, like I said, we've already proved that this thing is true. Okay? But now we're going to use mathematical induction to do it. And I'm going to have a very specific way that I want this done. So, like, your book is going to give you something like this, and it's going to say, prove that the statement is true for every positive integer n. And what I want you to do is, given that in that prompt, that you do this right here. You start by writing theorem. Because a theorem, what is it? Do you guys know what a theorem is?
Like a statement
With?
with
Proof.
oh.
That's all it is.
Oh.
A statement with a proof is a theorem. So, for all n positive, so in other words, for all positive integers n, all of yours should look like this. Okay? You write theorem for all positive integers n. Then you state the thing that you want to prove, which in this case was 1 plus 2 plus all the way up to n is equal to n times n plus 1 all over 2. So that's your statement that you are trying to prove. Under that, write proof. Now, just so you guys know, usually, as if you take a proofwriting class, this is the way they're going to tell you to structure it. And what's really good, you don't have to do this, but it's very good to do, is you tell the type of proof that you're about to give. Because if you just start rattling stuff off, like, if you don't know what type of proof the person is about to give, you might start going down the wrong road. So very often, almost always, if somebody's going to do a proof by contradiction, they'll start off their proof by saying, we give proof by contradiction. Okay? Or if you're going to do induction, very, very often, you'll say, we do induction on K. Induction on K. This lets the reader know what's about to happen. And this is the variable I'm going to use. So if you remember, that second part of that statement was that if you show that PK is true implies that pk plus 1 is true. That's that second step. When we take that second step, I'm just letting the reader know what variable we're going to be using. Now, we could just say we give proof by induction. You'll see that a lot. But as you're first learning this stuff, we do induction on, and then you say the variable that you're going to use in this step. Okay? But we don't do the second step first. We're going to do the first step. And the way I was taught, we call it the base step. And so I want to see this. Base step. Okay? So again, theorem, you state the thing. Proof, you tell me that you're about to do induction, and you tell me the variable you're going to use for induction. And now what we're doing is we're verifying those 2 points that I had written up here. Okay? And we do the first one first. The first one is what we call the base case or base step. The first step is we're establishing that base. We have to have a base of truth before we start off. Okay? But in practice, what you want to do is, like, this is what your formal proof is going to look like. But in practice, what you really want to do is check the first few ones. Like, we're going to say, what happens when n is 1? Well, you have 1 equals, and it's exactly the stuff that I just wrote, right? Now, you might think, well, okay, but who cares? They're telling me to prove this. It's got to be true. Like, I mean, like, do I really need to check it if they're telling me to prove it? Like, no, you don't. But, and this is really important here. For the first couple ones that we do, it won't really help. But the harder of these proofs that you do, doing this as scratch work first might give you a hint on how to proceed. Because sometimes it's not going to, and we're going to see an example of one where it's like, I'm going to write some stuff up there and I'm going to go, I don't know what to do now. And I'm going to do a bunch of scratch work on the board, and we're going to see, like, yeah, and in that case, maybe it would work if we did this, but you know, like, but my point is, if you write the first few of them, and you verify, okay, what's happening here? Well, then this becomes this, this is this, and this is this, and yep, okay, they're all good. Sometimes actually going through these steps and seeing it will help you when you go to actually do the proof. Because sometimes you're like, I'm not sure what to do. Then you can look back and say, well, how did this change as we went from here to here? Well, I did this, and that's how it worked. Well, maybe if I do something like that over here in my proof, again, the more of these that you do, the more that you're going to see what I mean by that. But now, okay, we've established, like, yes, okay, they haven't just given me junk. This is something that looks like it's true. Let's prove that it's true. We need to prove the case, the base step. And I'm just going to say, when n equals 1, then, and I'm just going to rewrite this, but plugging in ones, right? So now I've done this like 3 times. 1 plus 1 equals true, 2, which is true, right? That checks out, okay? I don't, like, if it were a more complicated thing, right? If this were a more complicated formula and this were a more complicated formula, I would like to see that, yes, we could verify that that's true, but this one's simple, right? You could say, this is true. And so, and one way of saying this is, so the base step holds. It means, like, the base step is true. Okay, so the base step is true. So in other words, I'm not doing this like the book says P1 is true. You'll notice I don't bother with the P's and stuff as we're doing this, because you're never going to see that again outside this book. So I'm just like, the base step is true. Okay. Any questions so far? Okay. Now the second step, which is called the inductive step. Inductive step. Okay. Step 2. Now, this is what I want to see. So again, all of this is what I want to see. And then you say, when K, no, I'm sorry. Sorry. I was looking at the wrong thing. Assume, now, okay, assume that for K bigger than 1, because we've already proved it when it's 1, right? And now, this may seem a little weird that I'm switching between n's and k's, But you know, it's just like that is the statement I want to prove. Now I'm going to bring in a variable, something that's going to change. And so this isn't always the way it's done. Sometimes they'll use k here. Sometimes they'll use n for everything. I like to split things up and say k. This is also the way the book does it. So when you read other examples in the book, this is what they're going to do. And so I'm going to stick with that. But assume that for k bigger than 1, and I'm just going to copy this thing down. This is the thing that I want to prove. Assume that this is true. Is equal to k times k plus 1 over 2. Everybody see what I've done here? Like, I've set this up to say, like, just like before. We have a P1. We showed that it's true. Now what I want is this cascade of P2s and P3s that goes on forever so that it's always true no matter what. But all I've done right now is I've proven this, and I can't just move to the next one because then I still have infinitely much work to do. But I'm trying to show that PK implies PK plus 1, and so it has to be general. I don't want to just say, well, let's move to the next one and do it. You know, like I was doing with the first ones, right? That's going, because that's not going to get anywhere. Then I'd have to do 3, then I'd have to do 4. Right now I'm saying, assume that this is true for some k that's bigger than 1. Okay? Everybody get that? Okay? Okay, okay. So now, again, we have to use somewhere, now this right here that I've just written, this, I'm going to circle it in red, this is called, you don't have to do this part. What's in red does not have to be on your page, okay? But this thing that I just wrote, the first thing that I wrote after once I wrote inductive step, this is what's called the inductive hypothesis. This is the hypothesis. It's like, let's just assume that this is true. Let's just say like that this does hold, okay? That's the inductive hypothesis. And this, in order to get what we're looking for, which is that PK implies PK plus 1, then somewhere here in my proof, I have to use this. I have to say, well, by the inductive hypothesis, such and such. Like, I have to bring that in somewhere. Otherwise, I have not done induction, and I haven't actually shown that this is the case. Okay? So, somewhere along the line I have to do that. But now I want you to do one more thing before we actually start to try to prove this thing. And that's, you don't have to do this. I mean, you do for me. But this was to help you out. So assume this, and now let's write our goal. We must show that, we have to show that PK plus 1 is true. So we have to show, what would this statement be if instead of it went up to k, if it went up to k plus 1? What would I write?
1 plus 2 plus
all the way up
k
to
plus k plus k plus 1.
Plus, and I'm going to use parentheses, k plus 1 equals what?
K plus 1 times
K plus 1 times, now, should
K
I use
plus-
parentheses here for k plus 1?
yes,
Yes, you better. Plus what?
k plus 1 plus 1.
K plus 1, which is...
K plus 2.
Yeah, there you go. Okay. So when you see those, and you're going to see them like this in your statement. In fact, I think there's one that's assigned to you like this. Okay. So this would be the statement when Pn is true. This is the statement Pn. That, well, I haven't written the full statement. So then n plus 1 would be 1 over what? If that's Pn, then Pn plus 1 would have 1 over
n plus 1 times n plus 2 times n plus 3.
There you go, okay? Parentheses are your best friend when you're doing inductive proofs, okay? Now, I have not finished this, that all has to be over 2. Not 3. Don't just start adding 1 to things, right? Like, oftentimes you do that, you're like, oh, everything's 1 bigger. Well, not that. That's not what that is, right? Okay? And so, okay. Now, we have to show that this is true. Okay? So I want to see that. You don't need to put a line there, but I'm saying, All of this has to be there. You have to tell me what type of proof you're doing. Tell me what variable you're going to use in the inductive step. Show me that the base case is true, and tell me the base step is true. Like, okay, don't just do this. Like try to communicate. Especially with this, you are working on communication. Tell me, like, don't just write that and be like, or better yet, don't write just that. Like, I'll know what you mean, but you're trying to communicate, okay? So let me know what's going on. Well, when n equals 1, that happens. So what? Why do I care? Why'd you plug in a 1? The base step holds. Oh, okay, we're moving on. Now, this first thing you write is the inductive hypothesis, okay? Now tell me, well, what's your goal? Now that you have your inductive hypothesis, what is your goal? What are you trying to show? That's what you're trying to show. This will help you when doing these. Trust me. You want this written on your page somewhere because it's going to get really messy and you want to be able to go, oh, there it is. I got it. I got the thing. That's the thing I'm looking for. So this is very, very helpful for you. Okay? So now, what you usually do, and especially ones involving polynomials, which these are, especially if you think of these as x's, right? Then what I like to do is start with one side and turn it into the other side. And so I'm just going to take a look at this and say, well, 1 plus 2 plus all the way up to k plus 1 is equal to, now like I said, somewhere in here you have to use the inductive hypothesis. So let's do that right now. I'm going to say, let's use, and what I want to see this written somewhere. As you're going from here to here, you're going to say, by the inductive hypothesis, we're assuming that this is equal to that. So let's replace this part right here and say, okay, there's k plus 1, and that's all over 2. And now we're just saying that's plus k plus 1. Now, since I went ahead and wrote that out, I'm going to say, well, I need to turn that into that. Okay? Because that's what I'm trying to show. I've started with that side. I need to show that that thing is equal to this. I've used the inductive hypothesis. So hopefully, everything works out. Hopefully. Now, I notice that I have a denominator on one of them. Maybe if I get a common denominator, that'll help me out. What do I need to do to give me a common denominator over here?
Multiply it by 1/2. Or no, 2.
Multiply by 2. Yeah. There we go. Right. Okay. Now here's the thing. When you're doing these types, which is, I've only given you one that's not almost exactly like this, that is involving some polynomial looking thing equaling some other polynomial looking thing. They're all gonna, you could pretty much all of them just do that and end up over there. It's not too bad. And if you just keep plugging along, really, it's like, well, I don't know. Let's multiply this out. That would be k squared plus k plus 2k. How about plus 2 all over 2? And I'm running out of room, so I'm just going to do this way. That's the same thing as k squared. How about plus 3k plus 2? 2. Now what? Factor it out, and hopefully, it works, right? K plus 1 times k plus 2, which is what we wanted to show. Okay? And so that's what we wanted to show. And since I have it right there, like, you don't need to say, like, that's enough, right? Like, you could just write that and you're done. But now you're not done, because I want you to write one more line. Because now we've shown the principle, right? We've shown, in one case, we've shown that P1 is true. And we've shown that this one being true implies that the next one is true, because we've used it in our proof, yes? That was what we used. We didn't just take this and derive this willy-nilly, which we could have, because like we've seen how you could do this. Some of these you can't do all by itself, but you've used the fact that the previous one was true right here. And so now, that being true, in other words, what you've just said is that PK, we've just proved that PK being true implies that the next one is true. PK plus 1 is true. Now we get our cascade of P2 true, P true implies P3 true, and so on and so forth forever. So now state that and say, therefore, or thus. So you don't need to have all this. But the thing I want to see at the bottom of each one of your proofs is thus, or therefore, or thus, thus, and then you just write this. So 1 plus 2 plus all the way up to n is equal to n times n plus 1 over 2 for all n being positive. Done. Okay? It seems like I'm asking a lot of you, but I'm telling you, as you learn this stuff, keeping this stuff like this, when you get good, it's like, who's Louis Armstrong? You guys know Louis Armstrong,
Yeah.
trumpet player, right? And you know, like when he plays, his cheeks get like huge, right?
Yeah.
And like, if you've ever played a wind instrument, the first thing your teacher's going to tell you is you don't puff up your cheeks. You keep your, what's called an embouchure, right, or embouchure, and you keep your cheeks in. And I remember my saxophone teacher telling me, when you get as good as Louis Armstrong, then you can puff your cheeks out, right? Same kind of thing here. When you get really good at inductive proofs, then you can make it your own, and you don't have to follow this exact format. But while you're learning it, this is all here to help you, and to lock into your head that these are all of the elements you need. You need to have an inductive hypothesis. It needs to be used in your actual proof. You need to prove a base case, otherwise, like, how did we know it was true at the beginning, right? Like, you need all of these elements to come together in order for the principle of mathematical induction to give you that cascade of all of them being true, okay? And what's really nice whenever you're writing a proof is when you start a proof, say, this is the type of proof I'm going to do. And then at the end, say, the proof is concluded, and what have I shown? That this thing, that therefore the theorem that I was trying to prove is true. Just really good stuff to get in the habit of. Questions? Okay, get ready, because this one's really ugly. Okay, we're going to do the same thing. And I'm going to keep that there. Okay. This is number 4. And again, so this is number 4, and it says prove true for every positive integer and the statement is this: 3 plus 9 plus 15 plus all the way up to 6n minus 3 is equal to 3n squared. Okay, this is what's that's what's in your book. And so, I'm going to start by saying, theorem for all n. N positive, right? For every positive integer, I'm telling you, for every positive integer, this. Okay, so 3 plus 9 plus, I'm not going to bother with that, plus 6n minus 3 equals 3n squared. Okay? Okay, let's do it. Proof. We do
Mathematical induction.
we could just call it induction. On a variable. If you don't like k, you could use something else. Most of the time you'll see it's done on the actual variable here. It's not a good idea to get in that habit. It will mess you up, especially as these get more complicated. You're going to need to keep an n somewhere and bring in a new variable. It's just, yeah. So change the variables for that. So we do induction on k. So what's the first step? What's it called?
Base step. Base.
Base step. There we go. Base step. We're trying to establish that there is some truth in this. And like, let's do the first couple of them. So this is when n is equal to 1, 3, I guess it's just 3. Is that equal, is that true? Okay, is it true with 2, which is 3 plus 9? Is that equal to 3 times 2 squared? Yeah, okay, so that looks good. And maybe we do another one. These, though, doing that's not going to give you that much of a benefit, but... So, okay, base step. When n equals 1, then this formula is just a 3. And you can see that if you plug that in, right? This right here is the sum of a sequence. That sequence happens to be 6n minus 3, right? When you plug in a 1, you get a 3. You plug in a 2, you get a 2 times 6 minus 3 is 9. And so, yeah, that's just that sequence, right? Okay. So then that sequence, when n equals 1, is just 3. Okay, or the sum of that sequence is just 3. And then is that equal to that right there? Yeah. And so, the base step, you could say holds or is true or whatever. Right, I'm going to say is true this time, just kind of mix it up. The base step holds. What's the next step? What's it called?
Inductive.
Inductive. Now the inductive step. You could also see it called the induction step. Though it's a step, it's a type of step. What type of step? It's inductive. Okay, anyway. Assume that. For k bigger than 1, because we've already showed when k is equal to 1. So, just technically saying, so assume that when it's bigger, what?
3 plus 9, dot, 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 6k minus 3 equals 3k.
Yeah, 6k minus 3 is equal to what?
3k squared.
Okay. And what's this statement called?
Inductive hypothesis.
This is your inductive hypothesis. We're assuming this is true. And if it is, can we show that the next one is true? So we must show, if that's true, we must show what?
3 plus 9 plus 6 times k plus 1 minus 3.
Plus, yeah, and so, now here's the thing. It may or may not be to your benefit to keep that next term right there. Often, that is the case. But you'll want the previous one as well, right? But we need to show that that equals what?
3k plus 1.
The quantity k plus 1 squared. That's what we need to show. Okay, now let's get on it. So, and again, right, now another thing you could do, one thing you could do is you start with the inductive hypothesis. In this case, that's not, I think that's going to be a little bit harder on us. But like for instance, what we could have done, let's just as an aside here, the very first thing I showed, right, we started off by doing 1 plus 2 plus k plus 1, and then going along, and then at some point using the inductive hypothesis, and then doing stuff and stuff like that. What we could have done at the very beginning is said, at the very beginning, we could have said, well, by the inductive hypothesis, this is equal to k times k plus 1 over 2. Now I'm just going to add to both sides 1 plus 2 plus k. Why don't I just add k plus 1 to both sides? Then that gives me k times k plus 1 over 2 plus k plus 1. And we'd end up at the same place. Like you would find that that is equal to, remember that we were able to get from here to the thing, k plus 1 to k plus 2, bleh. Right? So you could use it, but somewhere along the line you have to invoke the inductive hypothesis. It just so happens that I think for most of these that are set up like this, it's nice to just start with this entire thing. And so I'm going to start with this side of the equation and say, and I don't like to just start writing stuff. I like to say something like, observe, check it out, watch what happens when I do this. If you don't want to do that, that's okay. I think it's cool. It's slick because you're like talking. So here's this thing that we need to use, or that this is the thing that we're trying to show is equal to this thing. So I'm going to say, okay, well, we could rewrite this. We could use the inductive hypothesis to get this equal to that. And that might make my life easier. So I'm going to say by the inductive hypothesis, this is equal to, all of this is 3k squared. Now we're plus 6k plus 1 minus 3. Yeah? Okay. Now let's just start multiplying some stuff out. And I get k squared plus, how about 6k plus 6? Right? 6k plus 6 minus 3. Like that.
And now we factor out well, 3.
So 3k squared, how about plus 6k plus 3? Now, what's really nice about having this here is I could just keep looking back up here and be like, does that thing, how do I get that thing into that thing? Well, there's a 3 out front. Can I factor out a 3? Yeah, I can. Okay, well maybe that'll get me closer to my goal. So that gives me a k squared plus 2k plus 1. And that is the thing! Okay, and so k plus 1 squared is the thing. That's what I wanted to. I just said we must show that this equals that, and I just showed that this is equal to that. And stop. Did you use the inductive hypothesis? Yes, you did. Okay, then you're done. We're done. Thus, there's my statement. Thus, for all, or we'll just do it this way, 3 plus 9 plus all the way up to 6n minus 3 is indeed equal to 3n squared for all n bigger than 0. Why? Well, because I showed it was true when n equals 1. And I showed that that implies that it's true when n equals 2. And so on, and 2 implies 3, and so on and so on. So it must be true for all n. We're done. Those. Okay? Okay. Get ready. We do not have enough room on the whiteboard to do the next one. Yeah, it's so bad. It's so bad. Okay, and I already talked about that. Good, so.
You can't flip this whiteboard.
What now?
You can't flip this whiteboard.
No, we can't. Okay, so I'm going to get rid of this. And I'm not going to write down the statement like the thing. I mean, I'm going to write everything down, but I mean like the problem itself. This is number 10. It's over here. This is number 10 from the book. And the statement that you're supposed to prove is that for all n bigger than 0, yep, that's it. 1 cubed plus 2 cubed plus all the way up to n cubed is equal to, can anybody guess what the formula for it is?
Oh, wait.
I bet you're wrong. Guaranteed. I never would have thought. N plus 1, 2 squared.
Oh.
Yeah.
I guess that
I don't think it does. Now here's the thing, right? If I told you to prove this, like in that one case, if I were to tell you, hey, prove this, right? And and you saw how we did it before, you might think, oh, there's that cool little trick where you add this one into itself backwards and it comes out to be this thing. And that's doable. You don't need an inductive proof to do this. But if I told you to prove this, you're like, maybe there's a trick. Good luck. Good luck. Yeah, maybe.
With 1.
I doubt it.
Yeah, okay, so now you have n cubed plus 1 cubed plus n minus 1 cubed plus 2 cubed. Good luck. I don't think that trick is going to work for you.
If you make n to the 1.5 squared, that would be...
If what?
N
to the 1.5 squared. Yeah, and good luck. I mean, that's what I'm saying. Like this is one where I have no idea how you would go about. I would probably square this out, and get some really ugly thing and then probably move around some stuff. I have no idea how you would do it outside of an inductive proof. So when you see something like this, prove this, you know you're in the realm of induction. Okay, and so this is, and so, okay, we do induction on K. We do induction on K. And so, in the base step, when n equals 1, we have this formula is just 1 cubed.
It's the same as oh,
1
because the square doesn't
over
actually
2 squared, which is, and now this is where I want you to, don't just stop there, like actually verify, right? That's the same thing as 2 over 2 squared, which is 1 squared, which is 1, and so base step holds. Now, inductive step. Okay? Here's my statement. Suppose that for all k bigger than, bigger than 1, we've already showed 1, so let's do the next one. For all k bigger than 1, suppose that it is true that 1 cubed plus 2 cubed all the way up to k cubed is equal to k times k plus 1 all over 2 squared. It is squared.
okay plus
Yeah? Is that right? Okay. Okay. So suppose that that's true. Now we must show what? Tell me what to write.
1 cubed plus 2 cubed up to k cubed plus k plus 1 cubed
Plus k cubed plus k plus 1 cubed is equal to
k plus 1 squared. Or wait, k plus 1, k plus 1.
k plus 1.
K plus 2.
Yeah,
K
k
plus
plus
2
2.
over 2 squared.
Now it is true that k plus, what we actually did here, it was with the k plus 1, we did add a 1. We just basically replaced everywhere that we saw a k, we just replaced it with a k plus 1. But that worked out to be k plus 2, right? So like if your formula is a bit uglier, like if you have k to the root k, or like k to the 3 or something, then you need to have a k plus 1 to the 3, or root k plus 1, or you know, blah, blah, blah. I mean, it could show up, excuse me, in crazy ways and blah, blah, blah. So that's what we want to show. And I mean, like, I already see where I'm going to use my inductive hypothesis. I'm going to use it right there. And so I'm going to start by saying, okay, check it. Check this out. This, and like I said, in this case, and in most of the ones you do, this is probably where you want to start. But not always. You could say, okay, well, that's true. And by the inductive hypothesis, this is equal to, all of that should be that thing right there. K times k plus 1 over 2 squared plus k plus 1 cubed. Now we got some work ahead of us. Because this thing, when I square him out, I get k squared, k plus 1 quantity squared over 4. And now if I need a common denominator, which is what I'm going to want, I need a 4 up here. Now I have a lot of work to do. Because this does not look anything like that. And this is a squared. That's squared. Okay. And so I better just start knocking it out. Here's my k squared. And this is the thing about these, is you know that, like, this should work out. They're not going to lead, they're not going to say, prove this, and then you can't prove it because it's not true in the first place, right? And with ones like this that are just big old polynomials, like you'll notice I didn't do any scratch work. I didn't bother to verify the first and the second ones. Like I just said, hey, it's fine, right? Like you'll want to do that with ones that aren't like this. So anyway, plus 4 times. Can anybody cube that out real quick?
K cubed plus, I don't remember.
3k squared plus 3k plus 1. That's the next thing we're going to talk about, the binomial theorem. Which is... yeah, and you got to use induction to prove it. So, yeah, there's reason to this rhyme, okay? Boy. Okay, so that's k to the 4th plus 2k cubed plus k squared plus 4k cubed plus 3. Oh no. 4 times 3 is 12k squared plus 12k plus 4. All over 4.
Factor out.
Can't factor out anything from that. And so that's all over 4. And here we go.
Or separate it, like factor by grouping.
Well, here's the thing, right? Yeah, and this is, so let me just get to this point. So now I've condensed all the terms, because I was hoping, hey, maybe I could factor this guy out. And it looks like I can't factor that. Like, I was hoping that I'd have a k to the 4th and then a k squared and then none of those terms, so then maybe I could factor it easily. I can't factor that. But what I'm gonna do is this. This is on my page now. I have it, and I have it wrapped around. It's like, I've said this is equal to this is equal to that. So this is equal to that. And now what I'm going to do is say, well, if I could turn this into that, maybe if I just go and multiply all that stuff out, that's what it'll give me. So what I'm going to do, and this is a really slick trick, right now on my page, like right here, I'm going to put a little star. And what you've done is you've just named this equation. You've called it star. And oftentimes it's star. And you could have it like, that's just, I'm sorry, it's just the way it works in math, right? You have a bunch of stuff, and now you have some big equation that you want to refer back to at some point, and so you call it star over on the right-hand side. And then you do a bunch of other work and you say, remember star? Well, by star, this is true. And so that's what we're going to do. I'm going to name this thing star. And what this means is, like, when I say, hey, remember this, like, I could call it equation 5 if I wanted to, or equation number 1 or something like that. But this is just shorthand for saying this. I'm going to say this is equal to this is the thing that I'm going to call star. Okay? And now, further down on my page, so pretend that this, like I said, we need a lot of paper for this. So remember, on my page, I have that 1 cubed all the way up to k plus 1 cubed is equal to blah, 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 all the way up to there. Now, further down on my page, I'm going to say, well, now, let's work on this side of the equation. And if I could turn this into this, I'm done. So that's what I'm going to do. I'm going to say, okay, now, or also, or observe, or whatever, please use English, it's cool. Like, let me know that you're breaking and doing something else. Now, it's true that k plus 1, k plus 2 over 2, all squared is equal to, and we can do this a lot of different ways. I like to do it this way, k plus 2 squared over 2 over 4, which is equal to, that's k squared plus 2k plus 1 times k squared plus 4k plus 4.
And then we have to multiply that.
Which is, and now I'm going to do it like this. K to the 4th, 4k cubed, 4k squared. Now this one jumps over and we get 2k cubed, 6k squared. 2 and 4 is 8k. Now it's a 1 times each one of those, so it's just k squared, 4k plus 4 all over 4 is equal to, and when I rearrange it, let's actually do it, right? We have 1 k to the 4th, so there's k to the 4th. Done. I have 4, 5, 6.
Yeah.
6k cubed. 4, And that is 10.
Uh-oh.
Oh. 10,
Oh,
11, 12.
Oh, no, that's supposed to be square.
No. We're missing.
No!
What do we do?
K plus 2 squared is K, 4K, 4.
Did you combine the terms wrong?
I may have.
Oh, on the first one. That would.
Like, is it 11k squared?
Oh, probably. No, it's 13K squared. Where did we go wrong? Oh no! 4K, 4K. 2K cubed. Oh!
That should be 8. Yeah.
Ah! 2 times
Okay.
4 is 8! Aha! Woo! Okay. 4. And so 8 and 4 is 12. 13. Oh yeah, like I said, this may be the hard, depending on how you think, this may be the hardest thing we do this year for you. 8 plus 4 is 12. Plus 4. All over 4. And now, okay, so we've showed that that's equal to that. And so I could say by star this, and like state what you've just done, please. Like say by star k plus 1 or k plus 2 over 2 squared is equal to this thing. 1 cubed up to k plus 1 cubed as desired. Which is what we wanted to show, right? That's what we wanted to show, was that that thing was equal to that thing, which is what we did want to show. And so sometimes you do want to work from both directions here, but try to do it like well, right? And like there's no way I was going to factor this thing down into that. There's no way, right? So
But do the steps work in the when we did the other thing, you couldn't.
right, but as you can see, each one of these steps does work in reverse, right? If you're dealing with inequalities and stuff, that's where you really have to worry. But each one of these works in reverse, and so you're good to go. Usually, if you're trying to turn one side of the equation into another, it's best if you could just do it directly. But this, good luck. I mean, you know, and so as long as each one of these steps works in reverse, which it does, right? This
no form.
equals this, which factors back into this, which is that, which is that.
Is there a formula to factor giant thing, like a quadratic formula?
Then there's no, once you get to the 5th power, there's provably no way to do it.
What if you squared the quadratic formula?
I mean, yeah, but then that would have to be a quadratic square. It would work in this case. It would work in this case, but since that is a quadratic, because you multiply it out and you get k squared plus 3k plus 2, and then when you square it, you would get this. And so there would be, good luck. I mean, like, it seems like way harder than operate on this side until you multiplied everybody out. Then multiply everybody out on that side, show that they're equal, you're good to go. And so, okay, well, and then finally, so therefore, thus, and now this is the very bottom of your page, you say thus, the thing that you wanted to show. 1 cubed all the way up to n cubed is indeed equal to n times n plus 1 all over 2 quantity squared. Done. Okay. Ah! Okay, we're late, but here's this is gonna be brutal. Like as if that weren't bad enough. But you see, like that's just algebra, right? That's just you're multiplying stuff out. There's nothing conceptually hard about that. It's just a pain, right? I'm gonna try to do this quick, and you only have one of these. And so maybe I'll try to do this down and dirty. This is what you're trying to prove. For all n bigger than 0, 1 plus 2n is less than or equal to 3 to the n.
Oh no.
Oh, it's terrible. It's terrible. Now you only have one of these. This is number 16.
3 to the.
Doesn't look that bad. But
Yeah, okay, good luck. So, here we go. Base step. So proof, we do induction. we do induction on K. Base step. When
1 equals.
n equals 1, then we have 1 plus 2 to the 1 less than or equal to 3 to the 1.
Yeah.
That's true if and only if 3 is less than or equal to 3, and so base step holds.
Okay.
Now, inductive step. Suppose that for k bigger than bigger than 1, 1 plus 2k is less than or equal to 3 to k. We must show. What?
Do we need logs for this?
Hey, you know what? And this is what I was going to say. We must show that 1 plus 2 k plus 1 is less than or equal to 3 to the k plus 1. Now, I'm sure there's a better way of doing this than the way that I did. But I can't see it. So what I'm doing first thing I'm going to do is some scratch work. And I'm going to go, well, this is what I want to show. So maybe I'll play with this first and see what happens. Right, I want this to be true.
How do they do it in the phone? Do they? Oh.
Do what now?
How do they do it in the phone?
I don't know. This is an even.
Oh.
Yeah. That's 2k times 3. Ah, that's a 3 plus 2k, which is less than or equal to 3k. Right. Ah, but look at this. Because I know I need to use the inductive hypothesis somewhere. So somewhere along the line, I need to have this somewhere. That's almost that. In fact, I mean, like, I could have left it like this and said, hey, wait a second. That's the same thing as 2 plus 1 plus 2k, which is less than, right? This is what I need to show. And I notice, wait a second. Can I go in this direction? Can I say that 1 plus 2k is less than 3k implies that that's true? And so I'm asking myself, if I have something, is plussing 2 of something less than multiplying by 3?
Oh yeah.
It kind of.
Oh, not
But
always.
here's not always, because here's the problem: is that let's say I had. Is it true that 1/2 is less than 1?
Yeah.
Now, if I add 2 to this side, is that better than multiplying by 3?
No.
Wait.
Actually, yeah, that does work, doesn't it?
But it wouldn't like 1.
Okay,
Well, if you
okay,
did-
that works. But what about this? What if I had 1/10 and 1/11? That's true.
Yeah.
But if I add 2 here,
Yeah.
is that less
Maybe
than
like
that? Ooh,
Like
no.
3/11ths and
2/11ths,
3/10.
is that less than 3/10?
sorry.
Oh, I guess it does
Wait.
work. Oh, it's not
Always-
plus, it's plus. I'm sorry, it's plus 2.
So 12
Is plussing 2 less than
23
23 11ths.
Right,
Oh,
so
less than
23
3/10.
11ths, is that less than 3/10?
No.
Definitely not.
No! Oh no! But, let's think about the context of what we're doing here. We're saying, suppose that k is bigger than 1. And so, 3, we're talking about multiplying 1, or multiplying a third, or something like that, right? And so, what I'm getting at is like look at this. So, in other words, if I have some number, and this is the worst case scenario, is that they're the same number. And I could say, when is it the case that adding 2 to it is less than multiplying by 3? Well, if I bring this over, 2 is less than 2n, right? That's 3n. I multiplied by 3, it's the same thing as 3n.
Yeah.
Bring that n over and I have 2n. So as long as n is bigger than 1, and I can be strict here if I want. Well, a bit overkill, but as long as n is bigger than 1, I should be good to go. And is that bigger than 1 when k is bigger than 1?
Yes. Yes.
Yeah, so in other words, 1 is less than 3 to the k whenever k is bigger than 1. Now you see what I mean? Like scratch work?
Yeah.
Right? And so now, okay, since 1 is less than 3 to the k when k is bigger than 1, then, how did I do this? Then 2, oh, that's how I did it. 2 times both sides is that. Right, I'm just kind of working my way back up.
Yeah.
And now I'm going to say, well, wait a second. That itself is less than 3 times 3k. Yeah. And so, or rather,
So then,
and so, or no, I'm sorry, that's not how I said it. That's not how I did it. So then I said, okay, well, hold up, we're almost there. By the inductive hypothesis, this, so now now I've done all the scratch work. And this is what I'm gonna do for my proof. You see what I mean? Like, this is bad. This is really bad. There's probably a better way, because I doubt that they just give you something this difficult. But there's gotta be a better way. And if you could find a better way to do this, awesome. In fact, if you want to do this one in a better way, I'll give you extra credit. Like, if you could find a different way to do this, I will give you extra credit for it. But this is where I'm gonna start. I'm gonna say, when k is bigger than 1, then 1 is less than 3 to the k. Therefore, 2 is less than 2 times 3 to the k. And now I could say, by the inductive hypothesis, by the inductive hypothesis, 1 plus 2k is less than or equal to 3k. So adding this to this gives 2 plus 1 plus 2k is less than 2 times 3k plus 3k, right? All I did, I just added this to that side, added this to that side. Now watch what we got. That's the same thing as, what do I need to show? That is true? Okay, 2k plus 1, okay, so 1 plus 2k plus 2 less than or equal to 3k times 2 plus 1. 1 plus 2k plus 1 less than or equal to, that's a 3. 3k times 3, which is 3k plus 1. As desired. Oh man, that's just brutal. Isn't that brutal? Oh man. And thus, I'm sorry, thus 1 plus 2n is less than or equal to 3n for all n. Brutal. That's brutal. But I only gave you one of these, and the other ones are just, I mean, they're a pain because you've got big old polynomials to multiply out, but nothing as bad as this. And the one I gave you might not be as bad. You can also see how the book did it. They always have examples to go with each one of these. But this is what I mean. Like, it's not always straightforward. When do I use the inductive hypothesis? How do I bring it in? You know you have to bring it in sometime. So, yeah.